Okay, welcome back. In this video, we're talking about something that's known as principal component analysis. Let me write it down. A very powerful unsupervised technique, principal component analysis. It's a very powerful technique, as I said, usually abbreviated as PCA. You might have come across it before. And this is meant for problems where there is correlation in data. And we are able to somehow deal with the correlation. We can untangle that correlation in a meaningful way, and we can extract as much information as we can from that. And of course, you might be thinking that we talked about correlation in when we were discussing whitening, and we said we can whiten the data when there is correlation, right? But if we whiten the data, then usually what happens is like all dimensions become uncorrelated and there is nothing left for the principal component analysis. Here we are not doing that. What we're doing is we'll have this original data, and based on the data distribution, we try to infer a better representation, which high level means that we are going to look at can we do a better representation of this data as compared to my standard Euclidean basis. What is my standard Euclidean basis? Well, it is my x1 and x2 that I've been using all along. And what this represents is this essentially, right? E2, like the unit vectors, and E1, right? And this is my standard Euclidean basis. So my data is distributed according to that, right? And we are assuming the data is centered, and whether the data is normalized or not it depends on our domain knowledge. Might not be required here, might be required, and if it was required, then yes, we have it scaled, we have it normalized. All right, so let us begin. What are we looking at now? We have this original axis. The original data is distributed along like x1 and x2, right? And just by looking at the distribution of the data itself, right, I can tell that there can be a better representation in terms of the axis, right? Let's say I have some other data like representation that's represented by my V1, and this is like orthogonal, of course, bad drawing, but has to be a straight line, of course, and V2, sorry, right? V1 and V2. And you can tell that this is a better, or I would say a rather natural axis for this data, because like this, the distribution of the data is such that the change is happening along this direction, this like V1. And also there is like some change along V2, but not much, right? Very little is happening, very little action is happening along V2, and that looks rather useless in some sense. And even for certain situations, we can consider this as some like small random noise, because like all the action is happening in V1, which is my dominant dimension. Okay, so how does that help us? How does that really make it make this discussion meaningful? Well, it does, because what we can do is we can convert, or maybe we can visualize this in somewhat this way. Let's say this is my V1 and my V2, and of course like this, right? And this is what my data is. This is how the distribution of this data is in my new axis. And what I'm like initially, what we were doing with my input x, which is like two-dimensional, was something like this. So my x1 and my x2, it represents x transpose E1. From our knowledge of the standard Euclidean basis, we know that this is x transpose E2, right? We know that this is how we represent the coordinates in my standard Euclidean basis. And this gives us our standard coordinates x1 and x2. Now, what we are arguing that the standard Euclidean basis is not the natural basis for this data. So the natural basis is V1 and V2. So we'll have to define the coordinates in that basis, right? So coordinates in my natural basis will be like, how can we define them? So let's say x and V1 and V2 are my new natural basis. So somehow I should have a way of expressing x transpose V1, x transpose V2, right? And let us denote each of these by Z1 and Z2, right? So if we cannot, like, if we can get the natural basis, we can get the coordinates in that, right? And that's what we are using. And we have like X in my standard Euclidean basis, which gets transformed to this Z1 and Z2, which let's say may be defined as Z. So Z is my final transformed data, or maybe like the same data, I would say, in this new basis. Now, the only thing that I have to take care of is that as long as my V1 and my V2 are orthogonal, right, as long as they are orthogonal, which most likely they are, right, there is no information that I'm losing, and I can recover my X, because what is essentially happening to my X? Like some kind of rotation is happening to my X, right? I just like did some kind of rotation, if you can see here, and I still have the same data, right? So what can we, so like how can we extract, or how can we recover X? Well, X can be recovered something like this. X is like x1 e1 plus x2 e2, right? That can be, if we have like z1 v1 plus z2 v2, because it's the same data, so we can recover X, right? But the fundamental idea behind principal component analysis is that we will be throwing some dimensions, because there are certain dimensions that are not really adding a lot to the representation of the data, and they can be thought of as like some form of noise. For instance, like all the action is happening along V1, and so V2 can be thought of as like some noise and not really something that's helping us in our like the information that the data is representing. So for example, I decide to throw away the data along V2. That means I decided to throw away Z2, right? Because I'm thinking based on my data distribution that I'm not losing too much, right? So what I'm trying to say is that when I have X equals x1, x2, I did some rotation, which is essentially the transformation. I got z1 and z2, but I decided that z2 is not like contributing much, so I'll just like remove it. And so all I'm left with is z1. Of course, I've reduced the dimensions of my data, but of course some information is lost, because I cannot reconstruct X directly or exactly. So of course I can do this, like I can say X is almost equal to Z1 V1, because of course based on certain data distribution I came up with the fact that Z2 wasn't as important, right? So some information was definitely lost there, but here I still can reconstruct approximately X from Z1 V1, because like I have like this missing term Z2 V2, so that would be the difference there. But it's still mostly a good approximation of X1. We still have the important information intact. And this here is the fundamental idea of principal component analysis. Let's try to like really summarize these things. So what exactly are we doing? Step one. Step one is identify the dominant directions. So identify dominant directions. That's step one. And then step two is we have to throw away the small dimensions, right? So throw away small dimensions, throw away minor or small or non-dominant, whatever you like to call them, small dimensions. And how does that help us? Well, that can help us in two ways. And one is dimensionality reduction. This will like lead to, I would say, dimensionality reduction, which is always the case. So this is always true. Now, it can also help us in some situations to get rid of irrelevant information. It may or may not. Irrelevant information. And this is our hope. This is what we want. But this may or may not be true all the time. And so that's one of the drawbacks that comes into picture of the principal component analysis. And that drawback is essentially telling us that, First of all, this is unsupervised, so I don't have the answers to like my data, so I don't have the y values, right? And let's say the minor dimension was important in certain problems. For example, look at the health related information, and if you're looking at our data again, right? So let's say this data was distributed something like this, and I have like V1 and V2 is, so let's say V1 was the height. Oops, what happened? Let's say V1 was the height of the individuals, and this is like the blood sugar level. And I'm trying to predict whether a person is diabetic or not. And if I did input pre-processing, I did dimensionality reduction, I did PCA, I would get rid of that blood sugar, right? I'm going to eliminate that because I think it wasn't important in terms of the way I'm looking at my dimensions. And so the smaller dimension that I'm throwing away in this situation contains all the useful information from the perspective of my problem, right? So then I'm doomed in that case. So even if like we do not throw away this dimension, right, and we are still doing this principal component analysis, consider that like the longer dimension or the bigger dimension or the dominant dimension, which is height in this case, will be like, what we want is that should be considered noise. And then comparatively, the signal to noise ratio is going to be small because my signal is going to be the V2 here. So if we are doing that and not throwing like everything, then maybe we are like in a better position, right? So the best overall we can do is hope that we only throw away the irrelevant dimensions. And let's talk about an algorithm that actually helps us achieve that in most cases, I would say, right? So let's begin with that after looking at the drawback. So let's call the dominant direction V. So let's assume the dominant direction is my V. Okay. Now the coordinates in my Z, right, in the dimension that corresponds to V will be given by, right, Z will be given by X transpose V. We talked about that earlier. Now, what do we mean by this like dominant direction? Dominant means that the direction that has the largest variance, right? So I can define Z as the dominant direction if it has the largest variance. And how do I define that variance? Well, I define that variance by this expression, right? 1 over n summation of all the points, Zn squared, right? And if this is like as large as possible, because like variance, this is variance because mean is 0, right? And we want this expression to be as large as possible, right? And that is going to find the direction that gives us the largest squared coordinate on average, right? So let me write it down, largest squared coordinate on average. Okay, so thinking about the Zn squared, what is the Zn squared? The Zn squared is Xn transpose V squared, right? This term here, which is nothing but V transpose Xn transpose V, right? And we want to find the V that maximizes the average of this. So that means something that maximizes the 1 over n. I'm going to like substitute this with this, right? N equals 1 up to n, and then this is going to be V transpose xn transpose V. We can rearrange a few terms here in the sense that I can write 1 over V transpose, and then the summation can go inside xn transpose V, right? And if we bring this 1 over n inside, let me show you what I mean. 1 over n xn transpose V. You're familiar with this term. You know this, right? This is the covariance matrix of the data. And here, like from the beginning, we said the mean is 0. So this is already centered, right? Because this is the covariance matrix of the data, we can write it like V transpose sigma V, where the covariance matrix is positive definite typically. All right. So how does that help us? Well, the direction V that's required, right, that gives the largest spread, is the V that maximizes this expression. And what is the V that maximizes this expression? Let me write it down. Like, I don't want to lose the equations here, so I'm just going to write it down here. And so the V that maximizes this equation will come from my covariance matrix. So my covariance matrix will have some eigenvectors. Let's denote those eigenvectors as like V1, V2, let's say Vd. And each of them will have like these eigenvalues. And if we order these eigenvalues, let's say the order is something like this, right? And this is of course greater than 0. These are the eigenvectors and these are the eigenvalues. Okay, so these are these eigenvectors are the dimensions that have dominance, right? And the dominance is exactly in this order depending on my eigenvalues, right? And so the basis that rotates the data into this new form is this orthogonal basis that has like V1, V2, Vd, and so on. So, and these lambdas or these eigenvalues are the definite and symmetric values. So I can get the new dimensions, right? And how these dimensions help me is that I'm trying to find the one that has the maximum spread, because the eigenvalue for the first one, which is V1, is the highest in this order. And so my V star, the optimal, the maximum one that I'm trying to find from this expression here is going to be my V1. All right, and this is what we wanted. So the optimal for this problem is my V1. All right, so let me summarize this algorithm altogether in certain steps. So PCA is essentially find the covariance matrix and the eigenvectors, right? Once I have these eigenvectors V1, V2, Vd, and of course the eigenvalues associated, I'll have all of these. I'll have the orthogonal basis, and that's essentially what I needed in my, like, I needed an orthogonal basis that captures the fact that there is largest variance like along a certain direction. And so this is like the covariance matrix of the data. Okay, and the most dominant direction is going to be V1, right? So that's going to represent my maximum variance. And so let me define like these new coordinates Z in this like new basis. So this new basis is going to be X transpose V1, X transpose V2, V2, not X2, and so on, X transpose VD. Let's say there are D of them, right? And so this is my direction of decreasing variance in my new basis, right? Which is telling me that this X transpose V1 is having the most variance, right? X transpose V2 is the most variance for the data for which is orthogonal to V1. Then X transpose V3 is the max variance with respect, like max variance that is orthogonal to V1 and V2 and so on, right? So this is like max variance, this one, max. This one, max variance, that is orthogonal to V2, orthogonal to, sorry, V1, right? And then the third one is going to be max variance, that's orthogonal to V1 and V2 and so on. Okay, so next what we need to do is we are going to construct these dimensions and decide a threshold beyond which we don't want any more variance. So that's the usual, I would say, process, right? So we decide some k coordinates, like let's say we decided some k coordinates beyond which we feel that like they are not really giving us any more information in terms of the variance, and so we just stopped, right? So this is known as stop k principle PCA directions. So top k PCA directions. And how will we reconstruct X when we have decided we have top K? Well, again, it's going to be like almost, not exactly, as we said earlier, Z1 V1 plus Z2 V2 and so on to ZK VK, not ZD VD, right? And what is this telling us? This is telling us that there is going to be this like some kind of difference, right? Some kind of slack that is known as reconstruction error. And that helps us actually in determining how, how many dimensions are really useful. So this is an error because like we have some loss of information and we need to find these top k PCA directions that give the smallest reconstruction error. And this entire process is known as the Ecker-Yang's theorem, right? So let me just like put all of that together in a single slide. So I have it here. And this is how we found the principal components, right? Depending on this new orthogonal basis, that was nothing but the eigenvectors of my covariance matrix of the data with the eigenvalues ordered. And that helped me find the one that has the max variance, which was V1, of course. And we just like ordered them. That's it. And these directions gives the best reconstruction of data and capture maximum variance. Okay, as always, let's look at the application of PCA on digits data. Oh, here is the digits data. And as you can see, like most information lies along one direction. It gives a really good, I would say, separation in terms of like one versus not one, right? It is already giving you that separation, which is excellent. But the important thing here is to consider this graph here, which is showing percentage reconstruction error versus the number of dimensions that were considered, right? And as like just look here, like around 50 or maybe around 55, the maximum reduction in reconstruction error has happened. And after that, like very little reconstruction is happening. So maybe that's like kind of pointing us to the fact that these are the best number of components that we can actually utilize, because the rest of them are not really capturing, or like if we just like discard the rest of them beyond that point, we're not really losing a lot. That's what this is telling us, right? So based on this reconstruction error and the comparison with K, this like really gives us a good idea of like how many really dimensions, like how many dimensions do we need, right? And this is capturing the dominant directions of the data. Okay, like after all this discussion, we should always remember that this was the input pre-processing technique or the dimensionality reduction technique that was solely based on the fact that we were looking at the data distribution, and this might not be really capturing the dominant directions for f. And so we are like the target function. We already discussed that when we said that there are certain like drawbacks with this technique. All right. Having summarized the entire algorithm and also the drawbacks, let's quickly summarize these techniques. And so, of course, we talked about the linear dimensionality reduction. There are techniques that are known as nonlinear dimensionality reduction techniques that deal with like data distribution like these. So you can see that this is like a spiral data, and we cannot construct a linear form here. So we have to do, we cannot do linear dimensionality reduction. And like what this is showing is here, this like red thing over here, is that we can create a feature that is like calculating the distance to all points within the spiral. So that's giving you a high level idea of what nonlinear dimensionality reduction does. I would recommend seeing the text for more information. The second thing that we can apply, so these are like other learning aids that are available there, and if you're interested, you should go and check the literature. The second one is like hints or invariances and prior information. For instance, this involves like some domain knowledge. And for example, let's say we are doing some classification of trees. And so a tree like of this form is also a tree, but then a tree of this form, like which is like rotated, or like there is some difference in like symmetry and rotational invariance, is also a tree. So because I have this like prior knowledge of tree pictures, I can incorporate that in my data, and that's actually also one like learning aid that we should keep in mind when dealing with pre-processing. Removing noisy data. For example, there could be like many ways of removing noise. In digits data, I can use like the k nearest neighbor to get rid of like these noise. And let's say if I'm using, and now this depends on like whether this point will be treated as like this point here will be treated as noise or not, depends on the selection of k, right? If k is 5, right, it will identify more noise in the data as compared to, let's say I decided k to be like 122 or something, right? So those are some of the things that we need to keep in mind when we are removing noise from the data. And then finally, we have more advanced validation techniques in addition to the cross-validation that we talked about, which was like more so from the perspective of like one of the basic techniques. But then there are more convenient and more accurate techniques, like validation techniques that are given here. So if you're interested, you should definitely go and check the literature. But this is all about learning aids. This lecture summarizes all the extra techniques that we have that can be applied before we actually jump into the learning models that we discussed throughout the course. So that's it for this lecture. I'll just stop here and thank you.